Okay, so this is part three of the video series, and now we're going to take the equations from video one and video two and apply them into the system we talked about into video two. Um, so to start off, so we have the equation from a video one right here, and then we have also um, the equation from video two right here. Um, and we kind of just moved it just a little bit. So if we go back up, so this was the equation for video two. All we did was move the temperature over to one side, um, and then we get this. And the reason we can do this is we can say since let's have the system back up here. So if we expand it up as we go up, this would technically be T2 or a final temperature or anything of that sort. But what we can do actually is, actually get the eraser again, we can just get rid of these two right here. So we can say that our initial temperature, and then this is the temperature that we're quote unquote solving for or something like that. But this also makes it easier because now we can just put the general temperature into there, and we can say that dp over dz is equal to negative p molar mass gravity RT. So now that we have that, then we also get, so this is T1 actually because I just moved down there. And then what we have is these two down here, but we're gonna take them out. So if we're dividing by a division, essentially we're just multiplying by the reciprocal. So then the P is actually gonna go on top, and then our P1 will be on the bottom now. So this is just multiplied by that just to make it a little bit simpler and everything like that. And then this is still to this power right here, but what we're actually going to do is just like everybody else that's been doing it, we're going to denote just that whole thing as alpha, just so we don't have to keep writing negative r over cv plus r the entire time. So now what we are going to do is we're going to multiply this over, so then this P1 will go down to the bottom, so we can rewrite this here. So dP over dz equals negative P molar mass G over RT. So this P1 will go on the bottom now, and then we're going to multiply the two P's together. So the first P technically has a power 1, and then the other one has a power 2, or a power 2 alpha. So that's just this is gonna go to 1 plus alpha. So then what we can do from here is we can move the dz over to one side, and then move the p over to the other side, and we're actually going to take the negative p just to get rid of the negative. So then this is going to be excuse me. So this would be, we'll keep the dp over here, we'll do this step by step. So then the p will go away, but so mg over r t1 p, and then dz. And then from the dp, what we're actually going to do is we're going to get rid of to get rid of the negative, we're going to take the we're going to take like the negative up, so then it'll be p2 v1 minus alpha. Excuse me. And then we can just integrate these. Oh, this is negative. We can integrate both of these sides. So integrate it here, integrate it here. And then this is going to be from, like we set up here, the like starting pressure. So our P1, and then we can just say that's P final. So then we'll have from P final to P1, and then from Z final to Z1. And remember, the Z is just not necessarily in the between, but the Z is just the height difference, essentially. So from this top one to this bottom one is essentially just the height difference of it. So now if we integrate this out, it is -1 over, oh, that is not an alpha. That is not an alpha either. 1 over alpha, and then we get the 1 over alpha, and then we get p to the negative alpha, I believe, and then that is equal to mg over r t1 p, and then since there was no z in the original equation, it's just our z final minus z1, because we just integrated those back in. And then this is interpreted from p final to p1. So now we just have not general solutions, but we just completely integrated that whole equation. So now we can work with it further, and more stuff like that. So if we, this has a negative in front of it, doesn't it? No, it doesn't. Yes, it does. Yes, I believe so. Yeah, because when we got rid of it up here, divide it. Yeah, because when we divided it up there, since it was on the bottom, we had to negate it, because since it was on the bottom, that's why these are negatives right here. We didn't pull out this negative at the beginning. That was my mistake. I initially said that we got rid of this negative right here when we divided it out, but we didn't. We left it there. The reason these negate is because it becomes that 1 over p to the alpha, but then we can just make it p to the -1 minus alpha. So then going back to this, so we can get rid of the two negative sides, because those will cancel out. And then now we need to interpret it from p final to p1, but since the only thing that's there, we can do, so p final to the negative alpha minus p1 to the negative alpha, mg r t1 p z final minus z initial, or z1. And then okay, and then what we can do from here now is we can take this 1 over alpha right here and divide it, and then that'll just go on top, so then the alpha will be right there. And then what we can do next is we can move this p1 to the negative alpha to the other side, because we have this other p right here, which I believe I made a mistake again. Yes, so right here, when I moved this p1 down here, I didn't move the alpha, so it should be p1 to the alpha for all of these. So let me just put those in real quick, and then this is p1 to the negative alpha, so we can move that to the outside, and then once we move it over, the negative alpha will just cancel out, so then p final to the negative alpha is equal to p1 and then times alpha mg rt1, and then from there z final, z initial, and then yes, right. So from there, then we have in terms of p final, essentially just we have the negative alpha on the one side, but we can just again take the reciprocal of this. So if we take the reciprocal of that, then this just becomes -1 over alpha for there. And then now we have this in terms of the final pressure. But if we look back to the original equation, we can morph this. So the final pressure, we can plug this back in to the original equation. So we can take it as sort of, we can plug it in right there. So we can go ahead and do that. So if we do So our T final is equal to T1, and then we have, I believe, P1 on the top. Yes, P1 on the top, and then over this entire thing right there. And what we notice too is that the P's will also cancel out. So then what we're left with after that, so this P1 on the top will cancel out with this P1 right here. So we just have T1 times the alpha mg rt1 z final minus z1, and then this will be to the negative 1 over alpha. So this is all to the negative 1 over alpha, but in the original equation, if we go back up and look, we still have our alpha up there. So then if we do that, these will just cancel out. So then this negative 1 over alpha goes away. So now we just have this same expression in terms of our final temperature. So now we have, let me get rid of this. And now this is both of the equations in terms of our final pressure as well as our final temperature that we can quote unquote solve for if we have a given initial temperature and pressure and or volume, or we can say how high up we want it to go with the z, the change in z is essentially. So let's say we have a certain gas that we know the molar mass for, and everything like that. If it's in an ideal gas, then we can say, hey, it starts at this initial temperature and pressure. If we want to move it up 300 feet or something like that, that would be our Z final minus our Z1. And then we can plug in all of these numbers, and it'll tell us what the final temperature and final pressure should be, just by some simple manipulations of the ideal gas law and just some definitions. I mean, this only works for an adiabatic system that is also reversible as well. We have to keep that in mind, because as soon as you say, hey, we're heating up a system, or hey, it's not reversible, so like the pressure inside is not the same as the pressure outside, then it'll completely change the way that these equations that we just wrote up affect our final numbers. But yeah, so this was adiabatic reversible gases moving from one height to another, essentially, with it being an ideal gas.